So everyone, I'd like to welcome Dr. Joseph Cook, who takes a big look at very small but micro biodiversity, hence not the double of small micro, because clearly that's the same thing. It is Sunday morning here in DC, so we're slowly getting going here. How are you doing, and where are we connecting with you from?
Yeah, I'm good, thank you. I'm in Margate, which is a little seaside town just about an hour and a quarter south of London. And
that sounds absolutely horrible.
Yeah, it's a nice day.
Seaside Britain. No, that doesn't sound, appealing in any way, shape, or form.
Yeah, yeah, it's not raining, surprisingly.
Okay, see, now you're just rubbing it in that you're seaside, rare, wonderful British weather. So let's talk about the cold then. Let's drill into that. Enough of this like imagining a beautiful British seaside. Let's talk the Arctic, Antarctic, all the above. Where is it that we're going to be going?
Yeah, all of the above. Mostly we're going to be focusing on Greenland, on the Greenland ice sheet. But what I'm talking about today potentially applies to all the ice on Earth, really, ice and snow worldwide. So that includes the Arctic, the Antarctic, the lower latitude, high altitude glaciers and snowpacks. But yeah, the focus is certainly going to be on Greenland, because that's where most of the work that I've done has been over the last decade.
Well, I'm excited to have you jump in and get to learn a little bit more. I know what your work is kind of the confluence of everything I love, science and technology, and strategic use of these two things together for bigger purpose. So I'm really excited. We got to meet, was it last year when you gave a presentation, and I got to see firsthand all the great work that you're doing. So I'm glad to be able to share it. So why don't you pull up your presentation? We'll jump right in, make sure we keep everything on schedule and on time. We've got a great day ahead of us. So while Joseph pulls that up. All right, looks like we've got some screen sharing. It's working. Everything seems to be.
You can see that okay?
I can see it wonderfully. It says Ice Alive, and then tothepoles.co.uk. I believe that might be the handle for people to also follow you, which is To The Poles, and learn a little bit about what you're going to talk about.
tothepoles.co.uk is my personal website, and at To The Poles is the Instagram handle if you want to interact with this after the talk.
Well, we know everyone, you got to get those socials out, make sure people follow it. I'll let you jump in and tell us more about what you do, and I'll talk with you after to some questions, because I'm sure we're going to have some great ones.
Okay, sounds good. Thank you very much. Okay, hello everyone, and welcome to my talk, Ice Alive. It's a real pleasure to be contributing to this Biodiversity Day Festival. A huge thank you to everyone that's been pulling this together and organising all of us explorers. It must have just been like herding cats. But it's turned out to be a really great online event, and I feel really lucky to be involved. My name is Joseph Cook. I'm a National Geographic Explorer, a Microsoft AI for Earth grantee, and a Rolex laureate. And I work on developing new tools and methods for predicting the melting of our glaciers and ice sheets as our planet's getting warmer. And right now I want to talk about an often overlooked aspect of glacier melting that ties in really tightly with the theme of biodiversity. So let's just jump in. We don't usually think of snow and ice as being rich in biodiversity. If you imagine being in the heart of the melting zone on the Greenland ice sheet, for example, or on the ocean-facing glaciers on the Antarctic Peninsula, or on the remote high-altitude ice on Kilimanjaro, or the snowfields of Alaska, you probably picture a barren, frigid, white landscape without many hints of life. And indeed, that's how many scientists and explorers have traditionally thought about snow and ice. Sure, there are large mammals like polar bear that migrate across the snow, and reindeer that feed around the edges, and muskox that live on the tundra, and there are hares and there are foxes, and the polar oceans are full of life, from corals and tiny krill right through to the giant humpbacks and blue whales and orca. But the glacier surfaces and the snow themselves, they don't seem like obvious habitats. And those hostile environments don't really offer much in the way of food or shelter. But if we look closely and consider creatures that are too small to see with our naked eyes, we discover a hidden universe, a microscopic frozen rainforest on the ice surface. And while those creatures are too small to see, their impact is too large to ignore. And in this talk, I'm going to explore this hidden ecosystem, and we'll discover why ice is alive and why we should care. So let's rewind back to the late 1800s, at the very start of the heroic age of polar exploration, when people were just first beginning to attempt crossing of the major ice sheets and discovering unmapped frozen worlds. The person on the screen is Adolf Nordenskjöld, and Nordenskjöld had sailed to Greenland to make an attempt at an ice sheet crossing. And his diaries contain detailed and really vivid accounts of his experiences, all the struggles, all the hardship, and all the discoveries made along the way. And on reaching the edge of the Greenland ice sheet, Nordenskjöld wrote in his diaries about a strange, dark, off-grey colour to the ice. And that colour surprised him because he expected the ice to be shades of white and blue. And as he started to make his crossing, he wrote about the trouble that he was caused by millions upon millions of these strange bucket-like holes in the ice that have a thin layer of black sediment on the floor. Some of them are tiny and some of them are meters across and meters deep. And there are so many of them, in fact, that he was unable to find anywhere to put down his sleeping bag at night. And he often found himself suddenly knee-deep in frigid glacier meltwater from accidentally stepping in or tripping over these holes. But being a curious scientist, Nordenskjöld was intrigued by those two features. Firstly, the darkness, the dark color of the ice, and the existence of millions of these little ponds in the ice. So he studied them. And astonishingly, especially at the time, Nordenskjöld realized that those two phenomena were both linked and that they were both biological. And under the microscope, he saw clearly that the material that was giving the ice this mysterious dark grey colour was actually a type of algae. And much of the material at the bottom of those holes was microbiological too. And his colleague, Dr. Berggren, was quick to document the various species that they found on the ice. And between the two of them, Nordenskjöld and Berggren, they named these species Ancylinema nordenskjöldi and Mesotinium berggreni. And Nordenskjöld's diaries from the time clearly demonstrate that he immediately saw the significance of this discovery at the time, because he described the algae as the greatest enemy of the ice, because they changed the color of the ice from bright white and blue to dark grayish purple, and darker materials warm up in the sun. And Nordenskjöld realized that this darkening effect would be causing the ice sheet to melt much faster. And in the image that you can see on the screen, you can see this darkening effect from a photo that I took from a drone at a field camp on the Greenland ice sheet in 2016, not far from where Nordenskjöld made his observations in 1875. And the dark color of the ice that you can see in the picture is the result of algae growing on the ice surface. And we all know that dark things heat up in the sun. If you've ever walked barefoot on black tarmac or worn a black t-shirt on a sunny day. So the ice is melting faster because of this biological staining than it would if it was clean bright. However, at the time that Nordenskjöld made this discovery, climate change and sea level rise, they weren't issues in the public consciousness. It was before the Industrial Revolution began to pollute the sky with emissions and humans really started to rapidly warm the planet. But now, with climate change being arguably the most pressing issue facing humans and in the coming decades, we've remembered Nordenskjöld's discovery and we're examining it in a new light, with a new focus on exploring and documenting the biodiversity of glaciers and ice sheets and understanding at a deep level their effects on glacier melting and on sea level rise. And right now, we don't account for this biological darkening process in our predictions for the future, which probably means that we're systematically underestimating the rate of ice sheet melting. So I've spent the last decade studying this process, right from early studies that documented what lives where and what processes the glacier microbes perform, right through to very recent studies, blending drone and satellite remote sensing and artificial intelligence and complex fieldwork, aiming to measure the microbial effects on sea level rise. So I'm going to share with you some of what I've learned along the way and try to sort of act as your guide on a virtual safari through this microscopic frozen rainforest so that you can see what lives on our glaciers and ice sheets too. So earlier on, I mentioned the bucket-like ponds that Nordenskjöld wrote about in his diaries. And they've got a name, they're called cryoconite holes. And that name comes from the Greek, meaning cold dust. And right now on the screen, we're going to take a dive into one of those holes. And as we get closer, we're going to pass through the ice surface and then through a layer of meltwater. And now we're under the water and we're going to get closer to the granules on the whole floor. And we see this sort of soil-like material that's full of microbial life. Get closer and we can start to see some of the microbes. These sort of pig-like things are called tardigrades, and they're the apex predator. They're the equivalent of the tigers or the polar bears in the macroscopic world. And then there are algae, fungi, and lots of bacteria, and the long stringy cells that you can see are a particular type of microbe called Cyanobacteria. And you can see them in this image as well. This is a real microscope image of some cryoconite that I collected from the Greenland ice sheet. And you can see those same microbes in this image. What we're looking at here is one of those stringy cyanobacteria. And these are really important because they act as the architects of cryoconite holes. Because they're long and rope-like, they can act sort of like fishing nets on the ice surface. And they trap bits of dust and debris that wash over the ice, and they bundle it up into granules. And you can see this process taking place in the next image here. See how these cyanobacteria have twisted around each other and started to form this microbiological net on the ice sheet surface. From this image, you can really imagine how a dense web of these could be trapping and bundling material that's washing over the ice. And at the same time, these cyanobacteria also produce a kind of biological cement as sort of as a byproduct of their photosynthesis. And that cement glues the granule together. You can see in this image that the fragments of minerals are covered in a sort of slimy substance. And this is mostly that biological glue produced by the cyanobacteria. And you can see it even better in this image. And the effect of this wrapping and gluing is that those granules become heavy enough that they settle on the ice surface instead of just being washed away in the meltwater that flows over the ice. And because they're dark, once they've settled, they warm up, and that heat energy is transferred into the ice and they melt downwards into the ice. And when they do that, they sculpt cryoconite holes into the ice surface. And that carves out a comfortable environment for the microbes to thrive in. They couldn't just live on the ice surface, but they can enjoy a stable, sheltered life on the whole floor with just the right amount of sunlight. And many other microbes can live there too, feeding on the carbon that's produced by those cyanobacteria as they photosynthesize. So those cyanobacteria are the architects of the ice surface, and they enable glaciers to have a rich biodiversity. And we refer to creatures that perform that function as ecosystem engineers. And a close analog in a different environment actually is termites. You know, just by going about their genetic predisposition to behave in a certain way, just by following their own life processes, the end result is to build a termite mound, which is a very complex structure that provides a habitat for lots of other organisms. And the same thing is going on the ice surface with these cyanobacteria. By going about their own life processes without forethought, without planning or intention, they're building a habitat that sustains biodiversity on the ice that wouldn't otherwise be able to exist. So we call them ecosystem engineers. What's really fascinating about the cryoconite holes is that they naturally expand to make sure the granules on the whole floor don't stack up on top of one another, because that would prevent some of them from receiving enough sunlight. Instead, not only do the microbes respond to changes in natural conditions, the actual hole does itself. When more material washes into a cryoconite hole, the walls expand. and the granules spread out over a new, larger floor area. And that ensures that the maximum amount of photosynthesis always occurs. So the habitat itself is changing shape to create the optimum conditions for the microbes that live in it. And even more incredible than that is that the holes themselves can migrate across the ice surface away from shady slopes and towards more evenly lit, flatter areas, maintaining the biological activity and promoting the biodiversity of the ice. And as they migrate, they can take on all kinds of complicated and interesting shapes, like the examples on the screen at the moment. These are holes mid-migration, and you can tell because they're not circular, not cylindrical. They're in motion off a slope onto some flat ground, making sure they're moving towards conditions that are better for the microbes that live inside. And also on the ice surface between the cryoconite holes and around the cryoconite holes, there exists another habitat, a different habitat. Algae can grow in very thin films of water around the surface of melting ice grains, forming a blanket covering across the ice surface. And those algae are special because they produce a pigment that's unique just to those particular algae that acts as a natural sunscreen. And that allows those algae to survive in the intense 24-hour daylight at the ice surface in midsummer. And that's crucial because those algae bake in the sun 24 hours a day in midsummer. And because the ice is very reflective, they get sunburned from all angles, not just from above. So this sunscreen pigment's essential for their survival. And it happens to have a dark purplish gray color. And because there are so many trillions of these algae, that has the effect of turning the ice dark purplish kind of gray. That explains Nordenskjold's observations of the dark ice from 1875. Now, this isn't just something that happens over a small area of the ice. It's so widespread that it's clearly visible from space, particularly in Greenland, where this biological stain can be seen as a distinctive dark stripe running along the western coast of the ice sheet, sometimes covering more than 10,000 kilometers squared. And generally, this stripe has been growing over the past 2 decades. And a major question is whether it's going to continue to grow and continue to accelerate Greenland's melting into the future, and whether in a warming world, the great sleeping giant ice sheets in Antarctica will start to show that behavior as well. So using drone and satellite remote sensing data and detailed fieldwork, my team and I have conservatively estimated that up to 13% of all of the melting from the southwestern section of the Greenland ice sheet was attributed to the growth of these algae in summers 2016 and 2017. So this algal darkening effect is really significant for the amount that the Greenland ice sheet is contributing to sea level rise. And you get a good sense of this dark stripe, what it looks like from above in the image that's on the screen. This is a Sentinel-2 image, which is a satellite, European Space Agency satellite. And this particular image looking over the northwestern part of the Greenland ice sheet. And you're looking at 100 by 100 kilometers, 100 by 100 kilometer area. And you can clearly see the dark stripe there on the right of the screen. So far from being a lifeless place, we've found life everywhere that we've looked on glaciers and ice sheets. And we've looked in some very unlikely places. In the summer, when the ice sheet is melting, huge volumes of meltwater are generated. And as it flows towards the sea, it carves out enormous vertical pipes in the ice that act like a kind of glacial plumbing system for flushing the water out to sea. And in winter 2017 and 2018, when all the water for the summer had frozen solid, a team of cavers and I abseiled hundreds of meters into these pipes in search of signs of life. And hanging from the ropes, I gathered samples of ice that was hundreds or even thousands of years old. And my colleagues were able to extract DNA from those samples on site on the ice sheet. And we were surprised to find that even here, locked away in ancient frozen ice in the dark, an active microbial system. Even in the most extreme corners of the ice sheet, the ice is alive. And it's fascinating to wonder if life can persist in dark, frozen pockets of ice like this on Earth, whether the same might be true elsewhere, of ice elsewhere in the solar system, like in underground caves on Mars, for example, or the ice of Jupiter's moon Europa. So what's next? Well, the current state of the science is that we've confirmed that the hidden biodiversity of glaciers and ice sheets is causing them to melt faster. In Greenland, this is having a significant accelerating effect on global sea level rise. We've gathered field measurements to show that the dark stripe on the Greenland ice sheet really is caused by algal growth. We've developed mathematical models to describe this process at the local scale and methods for detecting these algae from the air and from space. The next frontier is to build these processes into the big scale climate models and start to predict the effects of the hidden glacier biodiversity on future sea level rise. The frozen rainforest is a natural part of the environment like any other, and our mission is not to destroy it, even though it plays a role in global sea level rise and accelerated climate warming. These algae are just one cog in a fantastically complex climate machine. And fighting biological darkening directly is just tinkering when we should be reducing emissions and drawing carbon down from the atmosphere, making the machine run the other way. But in the real world, we're facing accelerating sea level rise into the next decade. We must account for the effect of glacial biodiversity if we're to make accurate predictions that lead to sensible decision making and viable strategies for combating the worst effects worldwide. Well, thank you very much for listening to my talk today. You can find me at To The Poles on Instagram or tothepoles.co.uk. And right now I'm going to hand back over to my host for some Q&A.
All right, thank you so much for the presentation and telling us a little bit more about the micro world that we don't even realize, I don't think we even realize is there in the Arctic and Antarctic. To think about a place that we think is so desolate and devoid of life being rich and full of it if you just look a little bit closer, and how much that is affecting everything we do and the planet as a whole. It's crazy to think something so tiny has such a big effect.
Yeah, exactly. And even 10 years after starting working on this field, being immersed in it for a decade, I'm still astonished by it. You know, we were saying earlier that I'm here in this little seaside town, and you know, when you walk from the train station up to my house, you walk all the way along coastal defenses that have been built specifically because this is a place that's vulnerable to rising sea levels. And I go and, you know, and fly out to a field camp on Greenland or whatever and look at these tiny microbes that are too small to see. But then you come home and the two things just they connect. You know, they connect by this mechanism of adding water to the oceans, raising the sea levels, and then it's threatening homes, it's raising insurance premiums, it's threatening agricultural land, coastal erosion, you name it.
Well, and that's a good reminder, I think, for all of us too, especially this weekend as we, you know, think about Global Biodiversity Day, how it's all connected. Like from these small algae that live in ice in Greenland affect even potentially me here in Washington, D.C. You know, rising sea levels will affect Chesapeake Bay, the Potomac River, and slowly work its way up to Washington, D.C., which sits right at sea level. In fact, it was actually an old swamp. So it's going to affect all of us.
Well, and the other aspect of this that links very tightly with biodiversity is that the microbes on the ice surface are turning over carbon. They're fixing carbon from the atmosphere, and then they're flushing that into the oceans, and that's seeding the base of the oceanic food web, not just locally around the ice itself, but at a big scale. So this stored biodiversity on the ice is fundamental to the biodiversity of the ocean.
Sorry, my mind is actually just a little bit blown right now. That's like, wait, that they're that connected, because I mean, we know everything's connected, but into that scale. So given how interconnected this whole thing is and what you're doing, what consistently surprises you? Because I feel like after 10 years, you're like, yes, I get this is all connected. I know you're still learning things, but what's been one of the things most recently that's surprised you that you're like, wow, this is what? I feel like you have a lot of those.
Yeah, for sure. And I think there's some experience like that every single year. Because because it's, although it's, like I said, although it's kind of a long history of this
Yeah.
research dating back into the 1850s, for over a century people just forgot. So in a lot of ways it's a very young field at the same time, because we've only just started to measure this and observe it in detail with modern instruments for maybe a decade. So even the sort of fundamental baseline data sets are surprising, because yeah, it's something that was written about a long time ago, but it's something that we're rediscovering. So even just what lives where, how many of these microbes are there, where do they crop up, that all of that stuff is surprising. But now that we're able to observe this from space and from
Yeah.
drones and from planes, we're seeing the scale. And I think the thing that really blows my mind is that these things are too small to see, but they're having an impact that's too large to comprehend. You know, this is happening at the scale of a continent, and but potentially more. I just recently, actually, just before the lockdown, I was in a different
Yeah.
type of isolation because I was in Antarctica, and and being out there, it was actually the first time that previously all of my work had been in the northern hemisphere, and going down and seeing
Yeah.
the sheer scale of the ice in Antarctica, and thinking
Right.
that as the planet gets warmer, Antarctica Antarctica could start to act like Greenland. Imagining the scale
Wow.
of the impact of that, where you've got seven or so meters of sea level rise locked away in Greenland, but 70 meters of sea level rise locked away in Antarctica. To think that it could start acting as sensitively to climate change as Greenland is quite a sobering thought.
That is, especially considering all of the other shifts that are happening into Antarctica. I mean, I remember the event where we met each other. We also had, one of your fellow fellows looking at, penguins and their shifting and how that whole ecosystem is really changing. And it sounds like you're looking at the very base level of that. What, and able to do that, you'd mentioned drones and space, and what technology has in the past 2 years really made this effort incredible, like easier, and made it so you can actually see the connection from that very small to the global scale.
Well, I think you've hit the nail on the head there. Really, it's about cross-scale linkages, and we've got lots of satellite remote sensing observations from all
Yeah.
kinds of different satellites, some of which date back decades, and some date back months to years. And piecing all of those together, I think that I think the real advances are being made in data fusion, where we're able to link what we can see on the ground and see
Right.
through microscopes or through sort of spectroscopic measurements and what have you on the ground, actually linking those to what we can see from space. And the bridge between the two comes from drones, because they give you the ability to look at a resolution of less than a centimeter, but a scale of hundreds of meters. Whereas with the satellites, you're limited to a scale of maybe
Right.
meters to tens to hundreds of meters.
Right.
And with your feet on the ground making actual measurements, you're limited to just a few scattered samples.
Yeah.
But the drone is the perfect thing for linking spaceball measurements to the ground-based measurements, and that allows you to cross-interpret one to the other and sort of distribute your knowledge that you're gathering from the ground across the entire ice sheet. That's the
That's
big innovation. That's the big innovation that's taking our understanding to the next level.
and that to me is a great way to kind of wrap up and end too, is that it's all about that interconnectedness and being able to, take something that might seem small and have nothing to do with something large, and see that connection. And that's a big part of your work, and I know a lot of the work of other, people working in the field. So I definitely want to thank you for being here today and for the work that you're doing. And glad that you are on the front line of, connecting those microscopic dots to the global ones.
Okay, brilliant. Thank you very much. It's a real pleasure to speak to you.